Hey folks, today's topic is inverse trig functions and trig word problems, part one. That's what we call part one just because we're going to do some word problems in the next unit that are, because we get the law, sines and cosines are going to be more interesting. These are pretty much always 90-degree word problems. So inverse trig functions, I'm not going to spend a ton of time on because I don't think that they're hugely important to pre-calc, but I got to have them out there so that we can reference them when we get for my AP kids next year, so we know whenever we have to use it, we can talk a little bit about their domain. So when you take a trig function and you inverse it, if you work backwards, we have a problem because let's say that I went and looked at, do you remember when we did solving? How many different angles have this side length for sine? Well, there's two answers there. Well, when I inverse it, it's saying which angle is the right answer. And the problem is you can't have both of them be the right answer if we're trying to create a function. That's different than, it's kind of like, what's the square root of 49? Square root of 49 is 7. What's the solution to the equation x squared equals 49? That can have two solutions. So when I say sine inverse of 1/2, I can't have both of these be my answers. Anyway, so there's a long-winded, whenever you're going to do sine inverse, cosine inverse, or tangent inverse, they only exist in certain quadrants. Sine inverse only lives from there and there, quadrants 1 and 4. Arc cosine exists in quadrants 1 and 2. And arc tangent exists in quadrants 1 and 4 as well. Now, why they picked these to be the quadrants that they wanted to use, I'm not sure, but it does make sense that they chose these as possible quadrants because think about sine. What is sine in quadrant 1? Positive. What is sine in quadrant 2? Negative. Now, if you move into I said 2, I meant 4. Quadrant 1, sine is positive. Quadrant 4, sine is negative. If you move into quadrant 2, you'd get some repeating answers. So the sine value of, let's say, the 45 in quadrant 1 is going to be the same as the sine value for the 45 in quadrant 2. That's a problem because that means that when I inversed them, I would have one side length that would give me two angles. So anyway, these are the places where the trig functions can live. So if you want to go to your unit circle and add them, boy, I'm running out of room on the front. I guess you could try to squeeze them down here. I think I'm going to put mine on the back. So I'm going to add these to my unit circle right now. Actually, you know what? I'm going to add them right here. So let's go in green. Green works for sine inverse. And then green also is the same for tangent inverse. And then pink will be cosine inverse. And by the way, I guess I should have said this. So if you want to add those to your unit circle, or if you want to draw these on there, if you prefer to actually draw them, that's fine with me too. But maybe I'll add those next year to the unit circle. But another way that you could say this is arc sine. So depending on which textbook or which professor you have when you're taking an advanced math class, they might call it arc sine. I usually will say sine inverse. So sine to the -1 and arc sine mean the exact same thing. So find the exact value of each expression without a calculator. So arc cosine of -1/2. So this is similar to what we did when we were solving. So cosine is negative. Check, check. Cosine is 1/2. So I'm going to go to my special right triangles. Which one of my special right triangles has a cosine, an x value of 1/2? That's the 60. Now, if this was a solving equation, we would write down both answers as our solutions. But this isn't a solving. This is an evaluating a inverse trig or arc trig situation. So only one of these works, and that's why you have to then cross-reference back. We're talking about arc cosine. Arc cosine only lives in quadrants 1 and 2, so that has to be the quadrant that I want. So who is the 60 degree in quadrant 2? That's 2 pi over 3. Let's try another one. Sine is positive, so I'm going to go through, I'm going to check. Sine is positive in those two. Sine is also 1/2 of the special right 30 degrees. But we don't want both of them. We can only choose the one that fits with where arc sine or sine inverse lives. And sine inverse lives in 1 and 4. Well, we checked 1. We didn't check 4. So I now want to say who's the 30 degree only in quadrant 1? Pi over 6. Arctangent is -1. Now this is the one where you're going to want to go back. Well, tangent is negative, where x and y are not the same sign. Or you could look at these. Tangent is negative. Tangent is negative. But we want to pick the place where tangent was 1. So which one of our special rights had a tangent that's 1? Well, it's got to be the 45 because those have the same side lengths. 45. But now I need to cross-reference back with arctangent's domain. And arctangent only lives in 1 and 4. So I'm going to circle the one that's in 4. The 45 that's in 4 is negative pi over 4. Now this is another one of those sticky points where if you're being a sticky mathematician, look, this lives from negative pi over 2 to positive pi over 2. So most people would want to write who's the 45 in quadrant 4. They would say 7 pi over 4. Now look, just to be clear, I'm going to accept both of them. If your next math teacher doesn't accept that, then you're going to have to make that adjustment. But I'm okay with accepting both. The problem with writing 7 pi over 4 is if I wanted to get to 7 pi over 4, I'd have to go past that 90 degree all the way around back into this zone. This domain lives from here to here. So I can't go past that 90 degrees to get to the 7 pi over 4. What I can do, instead of going this way, I can go this way. So instead of going around to 7 pi over 4, I can just drop back to negative pi over 4. So like I said, I'm not going to care too much about which way you write. Those of you take an AP, you should be very precise here, and you should try to write the correct answer based on where the domain lives. You try the next 3. Okay, cosine is positive. Check and check. Cosine is root 2 over 2 with a 45, and cosine inverse lives in quadrants 1 and 2. So I'm going to pick the 45 in that section, which is pi over 4. Sine is negative. Check, check. Sine is square root 3 over 2 with a 60. But arc sine only lives in 1 and 4, so I've got to find the 60 down there. I would accept, I should say, an answer of 5 pi over 3. But the correct answer would be negative pi over 3. That would just drop down 60 degrees in the negative direction. And then finally, tangent is negative, where sine and cosine are different values. Tangent is square root 3 over 2. I always got to look that one up. That'd be with a 30. Tangent inverse lives in 1 and 4, so I've got to find the 30 in that section, but it's got to be, I would accept 11 pi over 6, but the correct answer is negative pi over 6. All right, let's talk about trig word problems. Let's just talk about word problems in general. So the angle of elevation versus the angle of depression. The angle of elevation of an object as seen by an observer is the angle between the horizontal from the line of the object between the horizontal and the line from the object to the observer's eye. So the angle of elevation is calculated from looking forward. What did I use? Green for elevation. Looking forward and then looking up. That creates this angle right here that we just created. That's the angle of elevation. Okay, might seem like no big deal. But now let's look at the angle of depression. The angle of depression is looking forward and then looking down. That creates the angle of depression. And the reason I want to point this out so much is people get this wrong all the time. So here's a person on top of a building. They're looking down at something on the ground. Where's the angle of elevation? That's easy. That's the angle of elevation. That's looking up at the person on the top of the building, from the person on the ground looking up at their friend on the top of the building. Where's the angle of depression? Well, lots of people want to say that this is the angle of depression. That is incorrect. No. False. The angle of depression is always measured from looking at the horizontal and then measuring down from there. This is the angle of depression. Now, what's interesting is the angle of elevation and the angle of depression actually are the congruent angles, but they're not going to be congruent if you draw them in the wrong spot. So you want this angle because it's inside of the triangle. I get it. The problem is that's not what an angle of depression is. So if I've got the picture of our cat here, my cat Archimedes looking at somebody's pet bird in their cage, the angle of elevation is this angle here. The angle of depression is this angle here. Now there's a right triangle that we could draw in here. You could see where the right triangle is. I could make this a right triangle. Or I could make this a right triangle. And what people want to do is they want to identify this as the angle of depression because it's in the triangle. Problem is that's incorrect. That is not true at all. Now, what is interesting about the angle of elevation and the angle of depression is that they are the exact same measure, like I said before. They're congruent angles. Anybody remember why? Parallel lines. They're both, they meet at a 90, so these are parallel lines cut by a transversal. What theorem is that? Come on, make your geometry geometry teacher proud. It's called the alternate interior angle theorem. That's why those two are congruent. Alternate interior angle theorem, more than you wanted to know. So there's my little breakdown. Make sure that you understand or that you draw accurately the angle of depression. Almost everybody gets angle of elevation correct. This angle of depression is where they get mixed up. One more note, when diagramming word problems, in other words, when you take the story and you turn it into a picture, you always want to start with most permanent objects. Start with most permanent, then move to less permanent. Draw the most permanent objects first. The sun, for instance, is the most permanent object. A tree is less permanent than the sun, but more permanent than a person standing on the sidewalk, okay? That's the way you want to think about it. Then, my other piece of advice, don't put in any numbers until after drawing the complete diagram. So wait, because people try to put in the numbers when they have the picture incorrect, and so they get themselves all mixed up trying to do too much at the same time. So we're going to do 4 story problems, 4 word problems. All right, a clothesline is connected from a window on one building to a window on the building across the alley. The clothesline is 10 meters long with an angle of depression of 17 degrees. How far apart are the buildings? So what's the most permanent? What are the objects in this story? There's 2 buildings. There's this clothesline, and that's it. That's it. So those are the permanent objects. So out of those three objects, what's the most permanent? Well, I don't know which building is more permanent, so we could probably argue they're both equally permanent. So here's one building, and here's the other building. I'm picturing like a 1920s or something like that, down New York building. I'm kind of looking down the alley between the two buildings. And then you've got one window. Here's one neighbor. Then here's the other neighbor's window. And they've got a clothesline between their windows, so that because they didn't have washing machines back then. So they used these clotheslines to hang out their wet clothes. So there's our clothesline. Now I've got a good picture drawn. I've got the clothesline. I've got the two buildings. Now I can start to add some numbers. First of all, we know the clothesline is 10 meters long, so I can add that. That's 10 meters. They also say that we have the angle of depression of the clothesline. Now remember, angle of depression, you always have to look forward and then rotate down. This 17 degrees is the angle of depression. Now what's nice, okay, does that make sense? Angle of depression. So what are we supposed to find? There should be an X at some point in this thing. How far apart are the buildings? So we're actually also trying to figure out, actually trying to figure out is how far apart are these two? So I want to know this distance. This is what I'm going to call X. So do you see the triangle in there? I do. I see a right triangle. The problem is I have an angle that's not in the right triangle, so I'm going to apply some of my geometry skills and realize these are alternate interior angles. Or I can think about this as the angle of elevation is the same as the angle of depression. So now I can take this picture, now that I've got everything figured out in the picture, I can now turn this into a math equation. So I see my right triangle. Let's see, what sides do we have? If this is my angle, I don't have opposite. So that means I have adjacent and hypotenuse. So I can set up who's adjacent and hypotenuse. That's cosine. Cosine of my angle, we know, is 17 degrees. Is adjacent, don't know what that is, over hypotenuse, which is 10. Then this goes back to, what was that, 3.4, 6.4, 6.3, 6.4, I think, where we tried to solve. There's only 3 different ways to solve a trig equation. Who's keeping X from being by himself? In this case, the 10. How's it connected? How do we kill it? Now I'm going to calculate what's 10 times cosine of 17. But before I type that in, I am going to always check what first. Hopefully you said mode. Take the 2 seconds to type mode in anytime you do trig. You don't have to worry about this any other time except when you're doing trig. And so I need to calculate something with trig. I check the mode first, and we get 9 point. I'm going to go 2 decimal places, 9.56. So how far apart are the buildings? 9.56. And because they gave us units, I'm going to expect you to give me back units. Meters. A golfer is standing at the tee and looking up to the green on a hill. So the green, for those people who don't golf, the green is where the hole is, and the golfer's trying to hit the ball into the hole. And so the green is that kind of like extra mowed down area. So the golfer is standing at the tee and looking up to the green on a hill. Now, when I draw one of these pictures, I don't draw anything until I read the story and think about the permanent objects. The golfer is standing at the tee looking up to the green on a hill. If the tee is 36 yards lower than the green and the angle of elevation from tee to hole is 12 degrees, 45 minutes, I'll explain that in a minute, but I don't want to get confused on that, caught up on some numbers when I'm trying to draw the picture. Find the direct distance from tee to the hole. Okay, permanent objects. We got the golfer at the tee, so let's just count the tee as the permanent object. We've got the green, which is up on top of the hill. That's it, right? Those are the permanent objects. So what's more permanent, the tee box or the green? Well, usually the green is more permanent. They can move the tee box around where you start from. I guess it really doesn't matter. In either case, I'm going to draw them just as dots. So here's the T. Then we're going to hit up to somewhere up on the hill. There's this green. Now, if you want to draw the earth, draw it all, you can draw all that stuff if you want to. I'm not going to draw any of that. They want us to figure out the direct distance from T to hole. So that means I want to figure out, so this is the T. This is the hole. And whenever they say direct distance, that's nice because it just means connect those two places. Now, do you see the right triangle? I can't see it for you. You have to see that. You have to recognize that right triangle on your own. I can see it. And it's right here. I drop a vertical there, and I drop a horizontal here. Now I've got my picture drawn. I've got my right triangle. So now I can start to figure out, I can start to add some numbers. So let's see what numbers we could add to this guy. Golfer standing at the tee looking up, there's 36 yards lower. So the tee box is 36 lower than the hole, so 36 yards would go here. By the way, when I drew this triangle, what kind of triangle did this turn out to be? That's a right triangle. That's important so that I can apply my trig. And then it says the angle of elevation is 12 degrees 45 minutes. So that's this right here. The angle of elevation is how far up it goes. So that's this here. But I got to talk about 12 degrees 45 minutes. Now, the only reason I want to show this to you is just on the off chance that you get stuck seeing it again somewhere, and I don't want it to be the first time you've seen it. So let's go up here. I don't know. Let's go from here. 12 degrees 45 minutes. That's how sailors used to look at maps, and they would talk about, instead of doing, I don't know why, but instead of doing, let's say 12.5 degrees, they would say 12 degrees 30 minutes. So the minutes is calculated just like out of an hour. So I prefer decimals because I don't know what 45 minutes looks like on a map. So I'm going to use my calculator. I don't have a minutes button here. So I'm going to convert those minutes into decimals. So this would be 12 degrees is the whole part plus 45 minutes. Well, that's 45 minutes out of how many minutes in an hour? 60. So you can either go right to your calc or just do the 45 over 60, doesn't matter. 12 plus 45 over 60 turns out to be 12.75 degrees. So 12 degrees 45 minutes is the same as 12.75 degrees. Now what's interesting is we don't have to do it on this problem. I just think it's kind of cool to talk about. You could also go down to seconds. Their next measurement after minutes was seconds. And that would look something like, let's go up here and do it at the top. 12 degrees, 45 minutes, and then 12 seconds. So if I was going to turn that into a decimal, I would do 12, that's already in degrees, plus 45 out of an hour would be 60, plus 12 out of, now, if I did 12 divided by 60, that would turn the 12 minutes into hours, but I need to then, no, sorry, that's 12 seconds. If I did 12 divided by 60, that would turn that into minutes, but then I'd have to turn that into hours, so I'd have to divide by 60 again, so you would just divide by 3,600. Anyway, you probably won't, I think you're going to see one on a partner quiz, and there's some on the homework that you can come back to. None of them that go down to seconds, but just for the excitement, the pure beauty of knowledge. You kids love to learn stuff, I know, so that's why I showed you that. Anyway, okay. So what trig function can we now, oh, I don't have a variable. Find the direct distance from T to hole, so exactly how far apart. So X is the hypotenuse. So what sides do we have? We have the hypotenuse, we have the angle, and we have opposite. So we have opposite and hypotenuse, that's sine. Sine of my angle, 12.75 degrees, equals opposite, which is 36. over x, which is what we don't know. This is root switchy. If you want to learn how to solve it that way, you would switch those two around. So I would get x equals 36 divided by sine of 12.75 degrees, which is something I would need my calculator to compute. 36 divided by sine of 12.75. We get 163.12. So those golfers out there, what do you think? What do you think the par is on this hole? Units? I'd say yards. Or not, I wouldn't say yards. It has to be yards. Don't forget your units. What do you think? Par 3 probably? 160 yards? Yeah, it's a par 3. Not a par 4. No way. Simon is standing on the street. His eyes are 6 feet off the ground. He is looking down at a cockroach on a box that is 1 foot off the ground. If he is looking downward at an angle of 40 degrees, how far is he from the cockroach? So, what are our permanent objects? We've got Simon. We've got the street. We've got the cockroach. Then we've got a box. Oh, the street and the ground, I guess, are the same thing. Okay, so what's the most permanent of those objects? Hopefully you said the ground. The ground is clearly the most permanent of those objects. Now next, you could argue what's most permanent. It's up to you. I would say probably Simon would be the next permanent. So now I'm going to draw Simon. Simon is 6 feet. His eyes are 6 feet high. So I don't get too complicated when I do my drawings. Number one, because I'm not a very good artist. And number two, you don't have to. He's looking down at a cockroach that's on a box. So there's some box on the ground. And on that box, there's a cockroach. Oh boy, this is really going to test my drawing ability. What do you think? Does that look like a cockroach? Looks like he's not even on the box. Evil cockroach? I kill you. This cockroach wants to attack you. Anyway, okay, so what are we looking at here? In the picture, we've got dude looking down at the cockroach on top of the box. So let's check from his eyes. He's looking down at cockroach. Do you see the right triangle? I do. The problem with this right triangle is that it's not all the way to the ground. So we're going to have to do some calculating. We're going to have to figure in the fact that this cockroach is on a box that's not directly on the ground. So now we can start to add some numbers. We know to Simon's eyes, we have a height of 6 feet. Looking down at the cockroach, 1 foot off the ground. So we know that the box is at a height of 1 foot. He's looking downward at an angle of 40 degrees. So that's an angle of depression. So as he looks forward and then looks down, that creates an angle of 40 degrees. Now, because of the alternate interior angle theorem, the angle of depression is the same as the angle of elevation. So I'm going to actually put the 40 degrees in here because that tells me then, or that's actually inside of the triangle that I'm drawing as a right triangle. How far is he from the cockroach? Now, that's not saying direct distance. That's saying how far he is away. How long would it take for the cockroach to chase him down? So that would be this distance there that we don't know. Now, we got to be careful here. I'm going to make one more adjustment. Inside of my triangle, I have this side. I have that angle, but I'm going to want to work with this length. The problem is 6 feet is not the length from the top of the box to the dude's head. It is how far? That's an actual distance of 5 because we have to subtract off the height of the box. All right. Let's go. Make a trig equation. So we have opposite and adjacent. So that's tangent. Tangent of my angle, 40 degrees, is equal to opposite 5 over adjacent x. This is the old switchy. So that's the same as x is equal to 5 over tangent of 40 degrees. 5 divided by tangent of 40 degrees ends up being 5.96, let's go with. 0.96, and then did it give us units? Yep, feet. 5.96 feet. All right, last one. From the top of a roller coaster 60 yards above the ground, a rider looks down and sees the Ferris wheel and the merry-go-round. If the angles of depression are 8 degrees and 11 degrees respectively, how far apart are the merry-go-round and the Ferris wheel? So that phrase respectively means that the first value goes with the first thing that they're talking about. So they're looking and they see the Ferris wheel and then the merry-go-round. So it's 8 degrees of depression to the Ferris wheel and 11 degrees to the merry-go-round. Well, do you see, we're supposed to figure out the distance between the Ferris wheel and merry-go-round. I'm going to call that distance here. This is what we want. I'm going to call that D for distance. Now, if you try to draw a triangle with just that, it's going to be this triangle right here. What's the problem with this triangle right there? It's not a 90-degree triangle, which means we cannot do SOHCAHTOA, which means we can't do our trig. Now, there is a way to do this with law of sines and cosines, or at least there's a possible way to do it. Maybe there isn't. I'd have to look. No, I still don't think we could do it with law of sines and cosines. So how are we going to do this? How can we find this? Well, I'm going to argue that there are two other triangles in this picture. Let's see if you can highlight the other two triangles. Well, there's a right triangle that goes to the Ferris wheel. Oh, never mind, the merry-go-round. And there is another triangle that goes to the Ferris wheel. And what we can do is we can then figure out, using the big triangle, we can figure out this distance from here to here. I'm going to call that y. And then I can figure out this distance here. I'm going to call that x. And once I figure out those two values, what can we do with those values to figure out the actual distance that we want? Well, then obviously we can subtract those two. So let's see what kind of angles, what do we need to add to this? So let's start with the pink triangle. So this is the angle in question. So I've got opposite, I want adjacent. So I have to figure out that angle. I can't have two variables. So do we know this angle? I would argue yes. Because of the alternate interior angle theorem, this angle is 11 degrees. The angle of depression is the same as the angle of elevation. So I can set up, that's opposite and adjacent. So tangent of 11 degrees is equal to opposite, which would be 60, over adjacent, which would be x. I can do switchy here. Switch the x and the tangent. So 60 divided by tangent of 11 ends up being 308.67. So x is approximately 308.67. Then I can do the same thing with the blue triangle. I need the angle here. This angle ends up being 8 degrees. And then I've got another tangent. Tangent of 8 degrees equals opposite, which is 60, over adjacent, which is y. switchy again. 60 divided by tangent of 8, 426.92. So y is approximately 426.92. And now I can take those two values and use them together to figure out what the distance between the merry-go-round and the Ferris wheel is. So that would be 42 minus 308.67, and we get 118.25. So the actual distance between the merry-go-round and the Ferris wheel is 118.25. Did we have some units? Yards. All right, so all these story problems, if you just waited and watched me do it, isn't going to help you too much. When you do a story problem, you've got to just jump in and go after it. Start with drawing the most permanent objects and work your way to the least permanent objects, and then put in the numbers, and then you can start to come up with an equation. All right, good luck.